From where we left yesterday. So, what did we find yesterday? Yesterday we had seen basically two steps to remember, that we first solved the least square problem and found a solution. Then which was a weighted least square problem in which we chose some weight matrix W. Then we found, then from among the solutions we found that if we choose W is equal to some RK inverse, then we find that the variance of the states is minimized, right. We did this for a single measurement V. Now remember that even if it is a single measurement, firstly remember that it is a vector. And in our treatment, nowhere it is for a general vector V. It so happened that it was Vk, but we can do it with respect to any other vector. The analysis as such did not assume anything, it just found simple least square solutions, I mean, to a linear vector optimization problem, nothing else. So the idea is that if you want to do the same thing with respect to all the measurements from V0 to Vk, then all we have to do is that we have to formulate a similar estimation problem involving measurements from V0 to Vk, exactly a similar linear vector measurement problem, and then solve it in exactly the same manner. So that is what we are going to do today. Okay. So first thing that we are doing now, previously we had found out x hat k that considers only Vk in the last day's notes class. Now we will find an estimate which will not consider only Vk, but will consider all Vk from V0 to Vk, right. So that is why we will solve a least square problem which will minimize the weighted sum of all these errors and then be minimum variance. So now first of all we have to write the system equations in a, previously what was our equation? Our equation was Vk is equal to Ck xk plus xi k. So Vk is, so the left hand side is the measurement vector, then a matrix Ck multiplied by the thing that we want to optimize xk, we want to optimize an estimate of xk plus some noise term. This was our form. So first of all, when we consider so many measurements, we have to again pose the problem in that form first. So now how do you, so it turns out that if you write this, we remember that initially in the last class we did it with respect to a single element. Now we are cascading all the elements, these may be individually, these may be vectors. So we are putting one vector, then the next vector, then the next vector, we are making a long vector. Okay. Now how do we, now first of all we have to write our, to be able to utilize our last day's results, we have to cast the problem in such a form where we will have the measurement on the left hand side as a vector, then we will have some matrix multiplied by the quantity that we want to estimate, plus some error term. You have to first put it in this form. So, so how do we put it in this form? So we apply the normal state transitions rules, that is what we are trying to say is that we can always write that, let us say we can always write like this. That is, what is the state transition relationship? Say our equation is, what is our equation? Our equation is this V is the, in this case this V is the one second. Our equation is like this: xk plus 1 is equal to ak xk plus gamma k xi k. Okay. So if it is like that, then then you can now and finally we have Vk is equal to Ck xk plus eta k. This is our system model. Okay. So now what we have to write is that we have to express these in terms of, in this form. How do we do that? This is again a kind of algebra where, so what we are writing is, this is, you know, this is a kind of symbolic form. This, what does it say? It says that, yeah, I have difficulty in writing. It says that V0, for example, let's take the first term. First term is V0, right? V0 is equal to what? Is equal to C0 x0 plus eta 0. Okay. Now if we have a concept of a state transition matrix, then we have, what do we have? That is, how do we write xk in terms of, x0? For example, we write x1 is equal to phi is equal to a0 x0 plus gamma 0 xi 0. Then we write x2 is equal to a1 a0 x0. Now x2 is equal to a1 x1 plus gamma 1 xi 1, right? So in other words, if you go on doing it like this, you will get that you will get x2 xk is equal to what? One second. You will get, right, correct. So you will get x2 minus a1. Let us get x2 from x0. Just let us put k is equal to 2 to understand. So we are getting x2 minus a1 gamma 0 xi 0 minus gamma 1 xi 1 is equal to a1 a0 x0. Correct? Now how do we get x0? What do we have to get? We have to get this one from xk. Remember that we are estimating x at time instant k, but we have to relate it to the measurement at 0. We have to go back. Okay. So so now here is an assumption that all these matrices are invertible. This we are assuming again, as I said right in the beginning, that we have to assume certain things. So what will this be? This will be A1 A0 inverse x2 minus A1 A0 inverse A1 gamma 0 xi 0 minus gamma 1 xi 1, correct. So now what is A1 A0? Now you can say that A1 A0 is a, now you see the, so you see that x0 is equal to this. So what is V0? So V0 is, I put this x0 here, so I will get C0 A1 A0 inverse x2 minus A1 C0 A1 A0 inverse A1 gamma 0 xi 0. Now A1 A0 inverse means A0 inverse A1 inverse. A1 inverse into A1 will get cancelled. So actually this term will be C0 A0 gamma 0 xi 0 minus C0, this will be A1 A0 inverse gamma 1 xi 1, correct. This is, so now you see that if your k is 2, then you have expressed V0 in terms of x2 and the noises xi 0 and xi 1, correct. Similarly you can write V1, similarly you can write V2. So if you now you can form a vector V0 V1 V2, and everywhere you are going back to x2. So in this case what will it be? It will be C0 A1 inverse x2 minus C0 A1 inverse gamma 1 xi 1. This will be what? This will be C0 x2. Now there is V0 is plus eta 0 is there. If you write V0, you have to write plus eta 0. So plus eta 1 plus eta 2 because of this term. So you see that you can, it is now possible, now you can, now this becomes your H matrix. So it is H into x2 plus some term which is a linear sum of the process noise components and the measurement noise, right. So these terms I have made an, this is the basic idea. So now therefore these terms can be expressed in this form. You see what is this HKJ matrix? It is C0 phi 0 k. So what is phi 0 k? Phi L k has been defined as from AK to AL minus 1, where L is greater than k. Now in this case A is less than k, because it is 0 k, k must be greater than 0. So phi k L, so phi L k when L is less than k is equal to phi k L inverse. So it is nothing but phi k 0 inverse. Now phi k 0 is what? Phi k 0 is A0, A1, A2, AL, AK, rather AK minus 1 inverse. So you see when you have k is equal to 2, then you have A0, A1 inverse, right. So in this way it will go, next one will be A1 inverse, next one will be I. So these are kind of inverse state transition matrices, if you know what are state transition matrices. This is just algebra. I mean I just wanted to show that it is indeed possible to be cast in that form. So the major thing is that you can write this problem into this linear form, in which we have already solved this problem. But this will now, if we now solve this least square problem and then choose our weight according to the see previously what happened here, what did we have? previous problem we had here, we had xi k, if you recall, and this one was our ck, correct? So now we are trying to solve this augmented problem. So we will do exactly the same thing. That is, after all, the least square solution, I mean, does not depend on the interpretation. As long as you have a problem in this form, you will get the same least square solution. Is it not? So therefore, now we can use our last result. That is, this is just what I proved just right now. The same thing written in general notation. Xk is equal to this. I did exactly that for that 1-2 case. So this we can skip probably now. So now we know. Now previously what did we see? We saw that if we choose Wkj equal to Rkj inverse, we get the optimal solution. What was Rkj? Rkj was variance of this in our last test problem. So now we have to choose variance of this as the optimal weight matrix. So we have to choose Wkj as variance of this term. There is a lot of algebra here today, we cannot help it. It is probably the simplest case. We cannot, so please bear with me and try to understand. Now this term is of this form, as we have already seen, that it will contain all these one eta term, and the rest will be all a linear combination of these past xi terms. This is what it will be. So there are two terms. Now the question is that if this is epsilon, what is variance of epsilon? So we want to find out this w. Imagine that, what are we trying to say? We are trying to say that if there is a stochastic vector A and if there is another random vector B, what is the variance of A plus B? That is what we are trying to find out. So now can you imagine what we are trying to do? You have a vector and we are trying to, so you know, one interesting thing about matrices is that if you break them into sub vectors and if you can write it as a block matrix, for example, this itself is a vector, but just for the time being treat it as an element. It is a vector, but just treat it as a scalar element. So then this matrix has this element, as if they are scalars. Then if you just multiply, then the same kind of results will follow. So you don't really need to treat them as vectors and get more complicated. So if you have, what is variance of A plus B? In this case, it will be variance of A plus variance of B. Why? Because these two vectors are independent. Because here we have, what were our assumptions? Our assumptions was that eta and xi are totally uncorrelated. So any of these terms, that is this and this, no correlation. And so now what is variance of A? Again we have assumed that each one of them are actually white. So therefore eta 0 is not correlated with eta 1, is not correlated with eta 2. So therefore when you take variance of A, you get individual variance of eta 0, individual variance of eta 1, their cross variations are 0. Even eta 0, eta 1 does not have any cross correlation. This is our assumption. In fact, to make them in this form, we have made those assumptions. Otherwise, I mean, the algebra becomes too complicated to solve. So variance of A comes in this block diagonal form. These are individually matrices because these are individually vectors. You have to visualize this. Okay. Now, Kalman filter is actually a recursive algorithm. So we have to see how we are not solving, you know, what is the problem of solving this problem? The problem of solving this problem is that as k goes increasing, this vector becomes longer and longer in length. So after some time it will become so long that you won't be able to compute the solution. So we are not going to compute the solution that way. So we have to have a finite fixed dimensional problem. Whatever equations we have must have constant dimension vectors. We cannot have a problem in which the vector dimension is increasing with time. So therefore we have to recursify it. That is, we have to compute our new solution based on our earlier solution and some constant computation. Unless we bring any algorithm in that form, it is not useful to compute in, especially in real time. So therefore our objective is that we have to recursify this form. We know the non-recursive solution, but it's not useful, right? So that's what we are trying now. Now let us see what happens. What is this? Remember, what is this WKJ? WKJ is the weight matrix when you try to solve for xk, taking care of measurements from V0 to Vj. That is why we call it WKJ. Correct? Because on the left hand side we have V0 to Vj and we are trying to solve for xk. Now let us see. Now we are trying to, we will go about recursifying it. So we will first note this identity. This is pretty cool because after all W is this inverse. So therefore W inverse is nothing but the variance. So what is W inverse kk? W inverse kk means I am trying to solve for xk taking measurements from V0 to Vk, same instant, and at every instant my measurement vector is increasing by 1. Correct? From V0 to Vk minus 1, then I am adding 1 Vk term at the bottom. It becomes a longer problem. Okay. So if I take the inverse of this, it will become a longer matrix. I mean the variance of this, because with the error term also one more block rows will come. So when you take the variance of that, then you will get for the first n minus rows, for the first n minus 1 rows you will get the kk minus 1 problem. The kk minus 1, k minus 1 means you are trying to take care of measurement from V0 to Vk minus 1. So you have V0, V1, V2, Vk minus 1. Now on the left hand side you have added another row Vk. So when you multiply it by its transpose, then you will get the block matrix and you will get one matrix corresponding to Vk transpose. That is the rather eta k, because a new row eta k will now appear here. So corresponding to that you will have rkk. So first thing is that this can be written like this. We have a long way to go, so don't sigh. Okay. I have tried to make it simpler than the original source from where which it is taken. Now remember our old solution. What was our solution? What is our solution? Our solution, if you recall, was finally after putting that RK inverse matrix, our first problem taking only Vk was Ck transpose RK inverse Ck whole inverse Ck transpose RK into Vk. That was the solution. So I have just put the corresponding ones. This is corresponding to Ck. This is corresponding to RK inverse Wk. So I have just put those things. This is Ck transpose RK inverse Ck whole inverse Ck transpose RK inverse Vj. This was our solution. Just put them in because it's the same problem, longer dimension. So this is my x hat kj. That is the optimal estimate of xk taking into factor measurements from V0 to Vj. This is my general solution. Now I have to recursify it, which means that I have to go from k minus 1 to k, then again from k to k plus 1, then like this I have to go, right? So essentially I have to put as j, I have to put k minus 1 and k and see how they relate. So that is very simple. Now from the previous two formulae that we have already obtained, that is this one equal to this, and hkk is nothing but hk. Look at hkk. What is hkk? Hkk will be C0 phi 0 k, C0 phi j k. So if you have HKK, you will have how many? 0k, 1k, 2k, 3k up to jk. So in this case it will be kk. If you have k minus 1, you will have one row less. Correct? So therefore you can always partition the matrix like this, and what is phi kk? Rather phi kk is 1, because to take the state estimate from k minus 1 to k, you need to multiply it by the matrix A. But is it not? What were we doing? We were multiplying. If you want to take x0 to x1, you have to multiply by A0. If you have to take xk to xk, you have to multiply by the identity matrix. So phi kk, it is a state transition matrix like thing. So between k and k, the matrix is I. So therefore here you have only ck, no phi, because phi kk is 1. So you can partition the matrix like this. HKK is this one plus one additional row. In this case, one additional column, because this is transposed. Actually it is like this. See, an additional row. And WKK we have already partitioned, that it will come like this. Because if this is W inverse KK, then WKK will be just treat them like a diagonal matrix as if these are scalar elements. So it will be the inverse of this and the inverse of this. These are the usefulness of block matrices. So then WKK is this inverse. Now you multiply this and you get, simply just multiply a diagonal matrix, so you get this term. So this term, see why I have tried to relate them? What is it that I have got? If I put x hat kk, I will get all these terms. That is, if I put j is equal to k, I will get this term here. Now I have to relate it with j equal to k minus 1. So if I put j equal to k minus 1, I will get these terms here. So I must be able to relate them. That's why I am trying to relate that how this matrix relates to this solution. So I have related and then found that this is the relationship, and this term appears additionally. I must go from k minus 1 to k gradually as I get new measurements, as I want to go in advance, that is from xk to xk minus 1. So all those I have to do. Okay, and so this part I have taken care of. Now I have to take care of this part. So this part now I am writing exactly in the similar way, that this part will be like this. Again, simply by partitioning. Multiply only this to this. So you get this into this plus this into this. That into Vk minus 1, and total thing is, in place of this vector, put this vector. This vector is Vk minus 1 on top and small vk at the bottom. So multiply these three, you will get this. So now this part I have related here, and this part I have related here. Okay, systematically only this there are a few matrices you have to carefully, keeping indexes maintained, you have to go and multiply them. So now if you find, now you put it here, that is this whole yeah. So now how do you get this? Yeah, so if you put k minus 1, put j is equal to k minus 1, j is equal to k minus 1, j is equal to k minus 1, and then on the left hand side, if you say this is assumption number 2. What was assumption number 1? That all the a's are invertible. That was assumption number 1. Now here is assumption number 2, that this is invertible. Previously also in our last problem also we assumed that Ck transpose Rk inverse Ck is invertible. Same assumption we made. So if this is invertible, you can pre-multiply this by this. So then this thing you are this thing you are pre-multiplying with this and you are adding this term. Now this into this, from this equation you pre-multiply this for j is equal to k minus 1. This will come here, j is equal to k minus 1 will be equal to this. So this into this is this term, and this is simply added, correct? Now this whole thing is what? This one. So this A, this total term I have called A. So this term is A, and wait, yeah, correct. Now this is, if you put j is equal to k, then this term becomes what? K, everything will become k, all the j's will become k if you want to solve for x at k. If you want to solve for x at k minus 1, in place of j everywhere you have to put k minus 1. This is general equation. So similarly you can write that just like you have written this one, that is this inverse this is equal to this. So you can write that same equation either for j equal to k minus 1 or for j equal to k. If you write it for j is equal to k, then you will get this into this is equal to this for j is equal to k. Now this, so exactly that's what I have written. Now this equal to a, see this one from this equation, this is a, the same a is here, this whole term is a. So what you are doing is, so you have, and so a is equal to this. So a into xkk is obviously this one, that is same equation I put j is equal to k. This is the same equation I put j equal to k, and that is equal to what? That is equal to, yeah, this one I have broken up. No. I am getting, I
the first term on the right hand side with k minus
this one,
no, on
this one, it is this one. See, I got this one, and this one I have already said that this one equal to this one. So I have just put it here. Now I am going to subtract. Here I have got a into xk minus k given k minus 1. Here I have got a into xk given k. I have to finally express xk given k in terms of xk given k minus 1. What am I getting? This is called the measurement update. That is, I am estimating xk based on measurements from v0, v1, v2, vk minus 1. That is my estimate x hat k given k minus 1. Given means given measurements up to. Now I get another measurement which is vk. So I have some more information. So ideally speaking, I should be able to estimate xk even better. So how do I now update my previous estimate x hat k given k minus 1 after I get a new measurement and make it x hat k given k? This is what I am trying to do. So I am trying to generate x hat k given k from x hat k given k minus 1 after another set of measurement vk becomes available to me. That is what I am trying to get at. Okay, because as I get more and more measurements, I should be able to refine my estimate more and more. So that is why. So now exactly. So now you subtract this and this. That is, subtract this from this. Simply subtract. Which terms will get cancelled? These two terms will get cancelled. So you will have this a, that is that old term, into this is equal to, so these two terms, as I said, will get cancelled. This one will get cancelled with this one. So they are same. So only these two will remain. So you get this, and then and from this you can just invert the other one. So you can write x hat k given k is x hat k given k minus 1 plus all this, that is this inverse this. You are basically multiplying by this inverse on both sides, pre-multiplying. So then this will go off. This inverse, A inverse will come here, this one, and then take x hat k given k minus 1 on the other side. This is the first equation of the Kalman filter, which says that if you had a measurement, if you had an estimate of xk given measurements up to k minus 1, and if you get a new measurement vk now, then this is the way that you must update your estimate to make it now optimal with respect to the set of measurements from v0 to vk. So basically, what have I done? I have solved one block problem. I have shown that if you solve this least square problem based on this block thing, first you solve it for k minus 1, then you include the new measurement, it becomes a longer vectors, longer matrices, then you solve it for k. If you get these two solutions of the same thing xk, then these solutions are actually related like this. This is what I have proved by lot of jugglery with matrices, nothing else. It is just algebra, painstaking, tedious, but simple algebra. There is no big concept in it. This is sometimes called the correction equation, because actually the Kalman filter is supposed to be divided into two parts. One part is called the prediction equation, where you go from xk to xk plus 1. That is, the estimate at which instant is the estimate, that you advance. Another is you relate two estimates at the same time step, but which take measurements, which take a new measurement into account. So one is a measurement update, which is called a correction equation, in the sense that you first obtained an estimate of xk without any measurement at the instant k, so only up to k minus 1. Then once you got that, then you correct your estimate once you get a measurement at k. So that is why it is sometimes called the correction equation, and sometimes called a measurement update, because this equation is executed once you get the measurement at vk. So it is a measurement update. So I have related this to this, but remember that we have still, that is, my estimate is at the same instant k, but if I have to go on doing it, then I have to advance k. I have to first make an estimate of x1, then make an estimate of x2, then make an estimate of x3. So I have to advance the first index. So how do I advance the first index? I have to advance time. Okay, here I did not advance time. I am in left hand side, right hand side, I am standing at k. So advancing time is again simple, involves matrices. There is one, see, interestingly, I mean there are two approaches. One thing is, going again rigorously. See, we have, I mean, one good thing is that we have solved the problem for arbitrary k and j. On the two sides of this problem, this basic problem that we have formulated, fortunately k and j are actually unrelated, in the sense that j can be anything between 0 to k. So that way I can write this problem for some value of k and some value of j. So exactly, one way is to again write these two problems for now k is equal to k minus 1 on one side and k is equal to k on the other side, and then try to relate them. That is a rigorous approach written here. But then before we come to that, let us get a sort of what is called a sneak preview kind of stuff. That is, just imagine that you are I mean you have some state, right? So you have, how is xk plus 1 and xk related? Ak xk plus gamma xi k. This is how it is related, correct? Now you have already made an estimate of this. That was your x hat k given k. That is the best estimate possible, because you have taken measurements up from 0 to k into account. You cannot get future measurements. Okay, so you have done all that you could in this. Now standing there without any measurement, you want to look forward, correct? So how do you look forward? Obviously, how does the system look forward? How does the true state get advanced in time? By like this, correct? Now, so obviously you will have to use this rule, but then what about this? The question is that here is something, it is, had it been simply this ak xk, you would have said that my estimate is xk plus 1 equal to a hat k, ak x hat k given k. If it was simply this, then you would have also applied the same rule, because there is nothing else. Now the only problem is that you have something else, you have this one. So the question is that can you estimate even a part of this? That is the question. But you cannot. Why you cannot? Because this xi, in this estimate, you have taken care of all process noise up to k minus 1, and you have already made an assumption that the process noise is uncorrelated, in the sense that xi k, you cannot get any information about xi k from 0 to k minus 1. That is the nature of the random process. So from your previous measurements of xi 0 to xi k minus 1, you cannot get any information about xi k. So if you do not have any information about xi k, what is the best strategy? Best strategy is to assume that it is in the mean value, because it is completely random. What is the mean value? 0. So still, even if this is there, under the assumption of that stochastic characterization, it is still best to just propagate through A. This is an intuitive picture. Now the same intuitive picture is actually, you can rigorously compute again those two solutions for k minus 1 and k, and then arrive at the same, see all this, because of the fact that you have to, what is involved is what is known as a matrix inversion lemma, which some of you might have studied in some other courses. A plus BCD inverse is equal to, there's a big formula, A inverse minus A inverse B transpose, vagera vagera. I mean, I don't recall what the formula is, I always look it up. So you can again go through that same thing and go on substituting all that, but finally you will get this. What we intuitively argued, that if you want to take, here is an estimate of x k minus 1, which you have generated using measurements up to k minus 1. Now you want to propagate the state up to k without having any additional measurement. So if you want to do that, you multiply it simply by ak minus 1. There is no better that you can do, simply because you cannot get any other information about the process noise from the past that you have seen. So all this mathematics, all these equations will finally give you the next equation of the Kalman filter, which is called the prediction equation, or sometimes called a time update, because here you are advancing time, and in other words, without any measurement beyond k minus 1, you are trying to predict the state at k. Therefore it is called a prediction equation. So either you have a predictor corrector formulation, there are various terms which are mentioned in the context of the Kalman filter, but these two are the basic state update equations. Now but the Kalman filter has many other equations. Why? It has at least 3-4 other equations. That is because of this. Actually these two are the basic state estimation equation are these two, this prediction equation and this corrector equation. But now people wanted to say that this GK also should be efficiently computed. again recursively, that is every time I don't want to solve, you see what is GK? GK is this A inverse this. Now what does A involve? A involves big quantities. A involves what is A? This one. Now you see these again increase in length as K increases. H increases in length, W increases in length. So you cannot compute A inverse using this equation. So therefore again you have to bring that into some constant computation time kind of form, right? So the rest of the equations of the Kalman filter are devoted just to make this computation of GK a constant computation which does not increase with time, because otherwise you cannot use it. So yeah, 5 minutes. So the question is how to update GK recursively. There is given GK minus 1, how to get GK from there using a constant computation at all K. So now again matrix algebra. Now this is just I have restated that formula, A inverse this, again written it for your reference. This is nothing but this. Let us give it a term called PKK. This is sometimes called the process noise covariance. No, not process noise covariance, state estimate covariance, state error covariance. Why? That we will see. But let us give it a name. We have given the name PKK because here also K, here also K, so we have given name PKK. So one thing is clear, that this is yeah and correct. Obviously if this is PKK, this inverse, remember that PKK is the whole thing including the inverse. So then PKK inverse is the inner thing, just this one. So obviously PKK inverse equal to, from this equation itself, PKK inverse equal to this equation. This follows from here to here. Now there is a matrix inversion lemma. Again, matrix inversion lemmas arrive in different forms. So again, matrix, this is nothing. It is a kind of matrix identity. People have said that A plus BCD inverse, if you do, it equates to that. It is an identity. It will hold for all matrices which commute. So no problem. It just happen. It's just a a cute observation which somebody made regarding matrices. So a lot of manipulation, putting this here, that here, taking left pre-multiplication private matrices common and all that. You can read it. You can try. This is not. I mean I cannot really recite these equations here. So finally it turns out that you can cast it in these two equations. This is just nothing but manipulation. If you see the notes, in fact I have tried to make it more simplified than the source. I mean the source from which this is adopted, that is Chui and Chen's book, none of these steps are actually elaborated. So it will say it can be shown, it can be shown, it can be shown, but I have shown for your benefit, spending some midnight oil. So finally you get this. This is nice. See, these are all constant dimension matrices. So at least there is an inverse here which is slightly nagging, but there is nothing whose dimension increases. So you have all constant matrices at each instant k, the same computation. Now there is as I said that these PKs are called state error covariances. Why? I mean I just took some arbitrary took some arbitrary formula of matrices and then named it PKK. So how I can tell that it is state error covariance? That has to be proved. So you can actually prove that, this proof is also given here, that variance of xk minus x hat k given k minus 1 evaluates to pkk minus 1. So what is this? This is state error. If you make an estimate of xk taking measurements up to k minus 1 and then take the error from the true state, then, and if you take its variance, then it will it will become pk given k minus 1. So therefore this is the covariance matrix of state error. That is why it is called state error covariance. Similarly, by exactly same matrix algebra, you can compute even k given k and you will get pkk, same thing, right. So final thing, there is only one thing remaining. So you see now what have you done in these equations? In this equation you have calculated from pk k minus 1 to pkk. See, using pk k minus 1 you have calculated gk, using gk and pk k minus 1 you have calculated pkk. So from kk minus 1 you have gone to kk. So again it is like a measurement update. Even for this you have to make a time update because everything must proceed in lockstep. So you have to now, final equation is that you have to take k minus 1, you have to get from k minus 1 you have to update this one. So that is very simple, that is because simply by observing these equations. So these two are standard equations. So you now compute xk k minus 1, this side you get k minus 1 k minus 1. Now if you have a vector which is like ax plus b, then the say y is equal to ax plus b. Y is a vector, a is a matrix, x is a vector, b is a vector. If you have such a case, then obviously variance of y will be a variance of x, a transpose. This is simple. So just from this equation you can get this equation, because the variance of this is this and the variance of this is this. It is very simple. How do you initialize this algorithm? You have to start it with something, because every time you have to give some basic estimate of x hat 0 given 0 and p 0 given 0, then you can take it up from k to k minus 1. So that is, here is this is your initial guess of x hat, you know nothing about it, you have no measurement so far. So therefore you have whatever is your mean estimate of your initial state, that you must put, and then p00 will become the variance of. So that's why I said that you need to make assumptions about the initial state as a random variable. You need to make an assumption about its mean and its variance. So that's how you initialize the algorithm, right. So finally we have made it in time, just in time, by skipping some steps. These are the Kalman filter equations. So you first initialize, then after initialization what do? Now you have no measurement, so from there you predict to x1. So from k minus 1 you predict to k. So first you apply the prediction equations, because you have no measurement so far, and similarly you update k to k minus 1 here. So these are your time update equations. Then you get your first measurement. When you get your first measure, in the meantime you calculate gk, then after you get your first measurement you correct these, and then again predict for the second measurement, and then again predict for the second time step, and then get the second measurement, correct it, then again predict for the third time step. This is the way you go on, and you get amazing results, as we will see in the next class. Thank you very much.